This is Professor Doug, and we are going to delve into Chapter 3 of Hibbeler's Mechanics of Materials. This chapter deals with mechanical properties of materials, and we will begin with a classic stress-strain diagram, and then we will solve other problems, all using Excel in this module, and show you that Excel can be very useful for solving stress and strain types of problems in mechanics of materials. In this first problem, we have data. This is not from Hibbeler, however, but it's typical of the material covered in Chapter 3. We have data from a typical tensile test. And for this test, we can see we have only 10 data points, data pairs, and loads from no load at 0 to 10,000 pounds. And 10 kips essentially, and then a sample with an original length of 2 inches and then a diameter given of 0.505 inches. So that's given and the original length is given. You can see with each successive added force of load to the sample, the length expands, goes into tension, and increases by about 6% from 2 to 2.12. during a 10,000 pound added load. So that data is plotted here on the stress strain plot for the sample. Now, how do we get a stress and strain from just load and length and area? Well, diameter rather. We need to calculate the sample area, and we're assuming it's a cylindrical, so it's 1/4 pi d squared with d given in inches, and the area then is 1/4 pi times this diameter squared. We get 0.2003 square inches. In order to get strain then, let's go to stress first. In order to get stress, we take each successive load and divide it by the area. So we're fixing the area. We're using the $ absolute cell reference, and we're taking each successive load and dividing it by that area. So we do that like so, and then we can just copy down the rest of the column, and we get our stress vector. For strain, it's just simply the length, the new length, or the change in length, minus the original length. So that's delta, which is lambda in some cases, divided by the original length. So that equation is just whatever the length is minus the original length divided by the original length. So that can be copied down the vector like so. And then the plot of that is just shown here with strain on the x-axis and stress on the y-axis. So stress depends on strain in this example. So you can see that a few things from this graph. We don't have a complete data set to failure, but we could pick out a few important points. The first one being the linear slope of the elastic region. And where we have a linear slope, it's about the first 5 data points. And then on the 6th data point, we start to get into a nonlinear trend. So I would assume that the proportional limit here is at the 6th data point, or somewhere between the 5th and the 6th data point, but we're not going to calculate that right now. We're going to separately plot the first 5 data points only here, and that can be done just by simply going to the first 5, highlighting the first 5, inserting a new scatter chart with a line connecting, if you know. But I wouldn't do the line, I would just do the data points, and then from the data points you would add a trend line. And then you want the equation, because the equation of this trend line is the slope of the line, which represents the elastic modulus, which you're trying to calculate. And the slope of that line is 9 times 10 to the 6 psi, which is 9,000 ksi. So that's the elastic modulus. It's the linear slope of the graph from the origin up to the proportional limit. And we use the first 5 data points for that. So from there, we want to calculate the yield stress, or the yield point. Well, that's a little bit more involved, so we have to use the 0.2% offset method. We take the strain vector, and that's the vector from column D here, and we just copy that down here numerically, and not the formulas, just the numbers. And then here we add 0.002 to each reading, and that becomes the offset strain vector. Then the stress vector is copied verbatim from up above. No formulas, just numbers. And now we can plot all 3 of these. Now, in order to do that, we would need to first plot the strain and the stress again. So we'll do that, insert a recommended chart here, and that would be a scatter with lines. We're going to pull that aside here, and then we can click on this graph and we can select data, and then you want to add data. Well, we're adding the first 5 values of the offset in the x-axis, that would be these, and then y values would be the first 5 values of 1, 2, 3, 4, 5. I think we didn't do 5 here, did we? Let's check this. Okay, let's see if that looks good. No, that didn't work for us, right? So there, yes, it did. So here we have that parallel slope. It has the exact same slope. We don't care about the y-intercept. It has the same slope as the first 5 points in the elastic region of the stress strain curve. Why do we do this? Well, we want to use the 0.2% offset method to extrapolate out this second slope in orange here of the offset up to the point where it intersects with the original stress strain curve. And that will give us our yield point. So we can do that by this method. We can add a trend, click on only the offset slope, add the trend line, but you're not adding a trend line, you're actually forecasting forward. So it's a very small amount of strain that you're forecasting forward. We'll start with 0.005 and see what that looks like. And you can see that's too much. We want to only intersect with the curve, so that's too little. So 0.075, probably a little bit smaller, 0.002 might do it. That's a little better. 0.075 or 0.085 might be better for us. No, that's not better. 0.001 could do, yeah, that's better. So now what I've done here is actually in a larger scale for you to see. We've intersected that, and the yield point looks like it's going to be 40,000 psi. Okay, so that's 40 ksi. So that's our yield point. So we've got a few pieces of information from this graph, and based on what I see here, the ultimate strength at the top would be this point right here, but we don't have any further data, so I would be remiss in calling that the ultimate strength, right? And we don't have the fracture strength either. So we know the elastic modulus with confidence, we know the yield point with confidence, and we can estimate that our proportional limit, sigma p sub L, is probably around 38 or 39 thousand. It's somewhere between this point, and that's something we're not calculating in this example. Okay, let's move on to another example. This time we are given a bone, okay, and the bone is put in tension. So the stress strain diagram is shown, and this is from Hibbeler's example 3.20, and it says determine the modulus of toughness. That would be the area under the curve, and the amount of elongation, that's lambda, of a 200 millimeter long region before it fractures if failure occurs at the strain of 0.12. So what I did here is I used a what if and a goal seek, and I set up a non-zero starter value for sigma. And we don't know what sigma is. It appears twice in this equation, so we have to use some advanced technique to solve for sigma. So for this, you would want the roots of the equation, and the real roots of the equation. There'd be 2 negative and 1 positive. We want the positive root. So that's going to be something that you can determine algebraically. But what we're going to do here is set up the equation that's given to us, 0.45 10 to the minus 6 sigma plus 0.36 times 10 to the 12th sigma cubed. That's here in this cell of epsilon. And we know that at 0.12, an epsilon value of 0.12, it fractures, it fails. So we want to know what sigma value will equate to an epsilon on the left side of the equal sign of 0.12. So it's as simple as just simply going to data, what if analysis, and you got a goal seek option, and a pop-up window will come up. And the goal seek here is we want to, actually that's not the cell we want. We want to set this cell epsilon equal to 0.12 left of the equal sign by changing sigma, and it'll solve for the roots. So you'll see some iterations that'll happen very quickly. And there we have it. So it's 6,861, and it gets us very close to 0.112. So from there, I plotted this, okay? And so I have 20 samples and 20 different readings, I should say, starting with epsilon 0 and ending with this value of 0.1194. So it's the same cell that you see here, right? 0.1194. And then I have sigma from 0 to the value of sigma that would solve the equation of epsilon equals 0.12. Well, I used a sequence here, 20 readings in a single column, and I used 343 because what I did is I took this value that was calculated by our what if analysis and I just divided it by 20 and I get 343. Okay, so this is linear even though it's not the case. Excuse me, but for each value of epsilon given here, which is nonlinear, then we get a sigma value all the way up to sigma max at 0.12 epsilon. So the reason I did this is just simply so I could plot the data, and that way I would use a plot that looks like this, and I already have it here, right? So I don't need to replot it. So I fit a trend line to this, and this trend line is just a moving average with a period of 2. And I did that so that I could see by trapezoidal approximation how many trapezoids are underneath the curve. And you can see, you can count the squares if you want. Each square is 1,000 kPa times 0.01 millimeters per millimeter. And then you would get an uneven number of squares because some of these squares are cut partially by the curve. So what I did instead is use trapezoidal integration. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 trapezoids, each with a base, or a height, I should say, of 0.01 millimeters per millimeter. That's the bottom of the trapezoid. The base 1 and base 2 are going to vary, and the first base 1 looks like it's at about, I'm using estimation here, 1,000, and the second base 2, first base 2 I should say, is about 2,800. You can see what I'm doing here. That means that this is the next B1, 2,800, and then for the second trapezoid, it looks like the B2 is about 3,500. And go on, each B2 is equal to the next B1. So that's something you could easily enter into Excel. The heights are all the same, and the area of a trapezoid is 1/2 B1 plus B2 times the height. So you just simply add up all the areas and you get 590.3. And the units are in kilojoules per cubic meter here in the SI system. Now, the actual answer is 613. So we want to see, like, how close were we? So I'm going to take the absolute value of 613 minus our value, which is 590.3, and I'm going to divide that by the average of the two numbers. So that would be probably easiest, just 613 plus 590.3 divided by 2. And we're pretty close. We are, if I look at this in terms of a percent, we are 0.9% off from our answer. So this is trapezoidal approximation. So we're not getting our actual answer, but we're getting fairly close by counting the areas of summing the areas of the trapezoids underneath the curve. And then the second part of the question is, what's the sample elongation of a 200 millimeter region before it fractures and a failure occurs at epsilon 0.12. For that one, it's just what you're just doing is multiplying the two values together to get 24 millimeters of elongation. Okay, the last problem, problem 322 in Hibbeler. Two bars are made of a material that has a stress strain shown. So you've got a compression graph and a tension graph on the same plot, and you can see that the maximum tension is the maximum tension stress is 5 KSI and compression stress is 25 KSI. So this material behaves differently. Determine the cross-sectional area of each bar so that the bars fracture simultaneously when the load equals 3 kips. So we're putting a 3 kip load here at point B, and we want to know what cross-sectional area of these bars would be that would result in fracture at 3 kips. So we put in the distance here. It's a 3, 4, 5 triangle. AB is 5. It's just by Pythagorean theorem. You can see that by inspection. Sigma max and compression, sigma max and tension are given on this plot. P is the load, and FAB and FAC, we don't know what those are. Those are shown in a free body diagram here, all right, of the reactions. Now, I'm going to use non-zero starter values for each of these of 1. You would not want to use 0. And then we set up our equilibrium equations. And I drew in the x and y vectors here in red and green, and also alpha or theta, I should say, the angle, so that we can see, how to resolve these vectors into their components, right? So what are the sum of the forces in the x direction? Well, you've got this FAB here, which is the force, reactive force in bar AB when the load is applied, and then you have FBC, which is the reactive force in bar BC when the load is applied, and then you have P, the load itself, and these are all in the XY plane. So we have 4/5 FAB. Why do we have 4/5? Because in X to the right, the green arrow, it's going to be the cosine of theta. Well, we don't know theta, so the adjacent over the hypotenuse is the cosine, so that'd be 4/5 based on the trig geometry here, right? So 4/5 of whatever FAB is the green arrow, or f of x to the right, and then FABX, and then we've got minus FBC, which is unknown, equals 0. And then in the y direction, we have, similarly, we have 3/5 FAB, because now it's the sine, it's the opposite over the hypotenuse of this angle to give us the y component of vector FAB. The blue vector is also a vector FAB. Minus P downward equals 0. So you got two equilibrium equations, two unknowns, and if I actually set the sheet up to solve for those 3/5 and 4/5 minus FBC and FAB, assuming that FBC and FAB are 1, or dummy values here in these cells, I just simply use the cell references to solve those, and they should be 0 because the bar is in equilibrium until fracture. They're not 0, so what do we have to do? Well, we have to use solver here. We have two unknowns, so we'll go into data and then solver, and our pop-up window comes up, and it says use the menu data solver, set the objective cell B24 equal to 0, so that would be this cell right here, right? B24 equals 0. You can type in value of 0 by changing FAB and FBC, right? And here they are, B20 and B21. These are the variable cells, subject to the constraint that B25 equals 0. So you can just type that in. B25 is also 0. So both of these equilibrium equations have to equal 0. They don't, because our values of FAB and FBC are dummy values. They're just 1 right now. We're going to calculate what they really should be, solve, and then solver will give us their actual values of 5 and 4. And then we can then calculate the cross-sectional areas by simply dividing the associated stress with each area. So we're taking 25 divided by 5, and then in this one we're taking 5 divided by 4, right? So here the member is in compression, so we use the maximum compression stress, 25, and here the member's in tension, so we use the maximum tension stress of 5 KSI, and the problem is solved.